Hi, everyone, and thank you for coming to our talk, Artificial Agents, LLM-Driven Bug Hunting and Patching in Open Source Software. We're going to talk a little bit about our submission to DARPA's AIxCC, the different components within it, how it all functions, and hopefully by the end of this, your thinking will be just a little bit more artificial. So first off, who are we? My name's Will Gibbs, as Alan had introduced. I'm a PhD student at ASU CEFCOM, former CTF team captain of Shellphish. I've also played a couple pwn-to-owns under CEFCOM T0, and I am the team lead, or the co-lead, of our AIxCC team. And here right next to me, we have Lucas Drazel, the PhD student from UC Santa Barbara, a Shellphish CTF team current code captain, and our AIxCC Shellphish co-lead as well. Shellphish is a multi-university team. I'm from ASU, so of course we have Arizona State University. We have Lucas from UC Santa Barbara. And then finally, we have several different people from Purdue. For our submission, this required a lot of effort from a lot of very smart people. Our team was about 26 or so people who you can see here who poured in blood, sweat, and tears to make it all happen.
And now, for me specifically, I'm also a big Matrix fan, so I bullied Will into letting me make the entire slideshow Matrix references. So what we're trying to do really is we are on today's mission. We're going to try to beat Agent Smith. And as everyone knows, first you should learn from your enemies. And one of the most important quotes from Agent Smith is, never send a human to do a machine's job. And that's what we're going to tell you about today, is how we did that. So to give you a quick introduction in the AI Cyber Challenge, in case you haven't seen the keynote yet, the AI Cyber Challenge, next slide. The AI Cyber Challenge is a challenge put on by DARPA and ARPA-H of the US. And it's really about incorporating next-gen based LLMs into cybersecurity analyses. The goal of the competition is to build a system that operates fully autonomously and can find bugs across a variety of different weaknesses. And of course, then at the end, we also want to patch those bugs in that open source software to really make that software more secure. Now, the target list kind of started for semifinals with 4 targets that we were given as examples: nginx, SQLite, Jenkins, and the Linux kernel. And as one might expect, those targets are actually pretty big and pretty hard. And so that kind of set the stage for both semifinals and now finals of where the competition is going to try to make us go and find real-world bugs in real complicated software. So for us, the decision of why to compete, the first one that you might consider is that obviously there was prize pool involved. So for qualifying to semifinals, the top 7 teams that advanced all got a prize of $2 million each. And in the finals, the top 3 teams got another set of prizes, $4 million, $3 million, and $1.5 million. So for a CTF team and a bunch of academics, that's obviously great. That's a great amount of money, and we wanted to compete for that. But that wasn't the only reason. We've been doing open source for a while. We've been doing program analysis for a while. We've been doing CTF for a while. And we really wanted to compete to create this open source CRS that can actually improve the state of the ecosystem that we're benefiting a lot from. And personally, we also just kind of wanted to learn how to use these LLMs as they develop throughout the competition and kind of really make sure that we're on the bleeding edge of seeing what these things can actually do. And lastly, there's a glory aspect, right? We wanted to compete in this because it's cool. Awesome. So we managed to qualify as one of the top 7 teams, which got us $2 million, which is a great start. And to do that, we had to solve a bunch of challenges. Now, I'm going to talk mostly about the finals challenges as they were given to us, because that's the current system that we're working with. Now, in the final challenge setup, as the first thing that Neo learns when he's trained by Morpheus, agents can be anywhere, right? Vulnerabilities can be anywhere. If you have a giant full mode Java app that is just a giant tarball of code and you have to find vulnerabilities, any single piece of functionality can lead to bugs. And something as benign looking as logging can all of a sudden introduce a critical vulnerability into your code stack, leading to the LDAP vulnerabilities in log4j. The second set of targets where we're given is what is called delta mode, where we're given a source code repository plus a set of changes to be applied to that repository. And we have to decide if there's vulnerabilities that lurk in those changes, right? If there's vulnerabilities that infect the open source software and try to turn it into something that can be corrupted or can be made malicious. Okay, to start off, this is a quick overview of our pipeline, just in the hierarchical setting. And we're going to first talk a little bit about how we can use static analysis to try to narrow down the candidates for this.
So as Lucas was saying, we're given two sets of targets. We have full mode and we have delta mode. Obviously, when you have a large project like the Linux kernel or nginx or SQLite, it's difficult to find bugs in hundreds of thousands, if not millions of lines of code. We're looking for the agent Smiths, the bugs that exist in those code. But it's really difficult to find them. So we need to start off first by narrowing it down. And how do you find agent Smiths? Well, first you start off looking for guys with sunglasses or guys in suits. And that's kind of what the first aspect of our pipeline was about, is static vulnerability detection. So we know that certain classes of bugs can be detected with static vulnerability analysis. We chose semgrep and CodeQL with several pre-canned queries that allowed us to very quickly find any sort of low-hanging fruit that exists, as well as encode maybe some common bug patterns that we can see in the source code. This is an over-approximation of the bugs that actually exist and will give us plenty of false positives. But the goal right now is just to narrow down the search space. Now, after full mode, we have diff mode, like Lucas was talking, or delta mode. This heavily scopes the challenge for us. Instead of having to look at hundreds of thousands or millions of lines of code, we can now just look at a few. There are two types of bugs that will really exist here. One is bugs that are introduced by the diff itself, which is relatively findable and a much easier task than the full mode counterpart. The second are bugs that are then uncovered by this new change. Bugs that were not reachable, but are now reachable due to the diff or due to the new feature that was implemented. The static analysis warnings in these regions of code are then prioritized much more heavily than any other low-hanging fruit that we'll see from our other static analyses. Another key part here is our diff guy. So because we're able to narrow the scope so much more in diff mode, we can have CodeQL queries generated to target those regions, to try and explore and find which functions are related to this ultimate diff that was produced. Can we find anything that's now newly reachable? Can we find anything that exists along the way that may help us get there? And so diffguy attempts to create CodeQL queries that will do exactly that. And then on top of that, after we retrieve the results from these queries, we then use LLMs to analyze, are there any bugs in any of these functions that exist that are related to this ultimate diff that occurs? Here you can see an example of an EXIF bug that's relatively easily findable if you're able to reach it. And then we aggregate this information. We have different sources. We have diffguy, we have CodeQL, we have semgrep that all tell us, hey, these locations are important. You need to look at these locations. And to actually figure out which ones we need to look at, we created a separate component, something called CodeSwipe. Now, CodeSwipe takes all of this information of which functions exist in the diff or which functions are reachable from CodeQL, what vulnerabilities do we think we've uncovered, and then assigns heuristic weights to them. This allows us to prioritize a small subset of functions in hoping to find the vulnerability quickly. Here you can see a quick example of what that might actually look like. This is a bug in a HTML handler. You can see that we've weighted it. All of the weights are 0 except for diff guy and for the diff base. We've identified, hey, this is something that we should actually look at.
Yeah. So once we have these code locations, then obviously we need to be, for the scope of the competition, we're required to also provide a proof of concept, a proof of vulnerability. We have to actually write an input that crashes this bug through one of the harnesses that we're given. So let's look at a couple approaches of how we do this. Now, if anyone that has done bug finding in the past or has been in this field for a while knows that when a new target is added, oftentimes our traditional analyses of libfuzz or AFL or traditional fuzzing tools can find bugs like no one's business. They run through the code, they find a bunch of bugs. But for this competition, while we can go through police officers like Neo and Trinity are doing, really what we're trying to do is find these harder bugs. And unfortunately, the next bugs that we're going to be finding, they're a lot harder to fuzz. These projects have been fuzzed for a while. These bugs have dodged every single thing we've thrown at them. And we really have to kind of step up the analyses that we do and find new ways of analyzing this code to find these bugs anyways. Now, the first way that we can do this is we can try to move like them. We can try to understand how they act. We can try to understand how the program behaves when this happens. And to do this, we rely on a fuzzing tool called IJON.
So IJON was a paper released in 2020 S&P, and the idea is to increase the type of coverage that your fuzzer can find. Initially, line-based coverage or bitmap coverage will tell you which seed or what seeds have actually hit which locations in the binary. The idea behind IJON is to expand this to not only line coverage, but to also include different states that are reachable. However, in order to do this, you need to manually annotate the code. So you get used to it. I don't even see the code. All I see is IJON min, IJON max, IJON set. We decided that humans weren't really necessary for this task. Let's try and use LLMs instead to add these annotations. So here's a quick example from the semifinals challenge of the Jenkins email plugin. Ultimately, it was reduced to this as a switch statement that was run in an outside while loop, where sequentially the programmer had intended you to execute these tasks to generate or configure an email, where going through logically, you go through steps of 0 through 5. However, the vulnerability exists when you break out of this cycle, right? The vulnerability here would show itself if you were to construct an email, case 0, set your email address, case 1, and then reconstruct your email or reconstruct the object at case 0. This was an out of sequence or out of order situation where the vulnerability would then be a reflexive attack that allowed arbitrary code execution. However, a normal fuzzer wouldn't really be able to find this vulnerability. It would be difficult because, as you noticed, we went back to line 0, right? Your coverage would already have said, we've seen line 0. We don't need to go back there. We don't care. So this is the idea or the intuition behind IJON to try and find these kind of stateful bugs to say, hey, I actually do want to go back there. Every time we see this case, if I see case 0 and then case 1, that's a new state. If I see case 1 and case 0, that's a new state. And ultimately, the idea is you annotate the code to improve the coverage and allow your fuzzer to explore more of these stateful concepts. The issue that arises is, why don't I just insert annotations in every line of code, right? If I do that, then eventually I'll hit all the stateful locations. The issue, though, is you end up with a state explosion. If you end up trying to instrument everything, then your coverage is almost meaningless at that point. Every single thing you find is then considered new coverage, and it's not really worth it. So what we did is we asked the LLM to identify potential state-changing variables in our prompts and other important or maybe suspicious-looking variables. You can see here that our IJON set crit, we've identified that crit is maybe something that we want to target, that if we see this change in value, maybe we want to say, hey, everything you see after this is new coverage. Or you can see our IJON max statement inside this loop, we want to maximize the iterations. We want to maximize the value of I in the hope that maybe we're able to get an out of bounds, right? The idea is that we want to annotate this such that we adhere to maximums or minimums or maybe unexpected behavior, and this is where the LLM can actually shine. So this was our more directed approach, but maybe for some of the bugs, for the diff mode, for the delta mode, this works very well, or if you have some nice queries from your CodeQL or SemGrep. However, in the general approach, it's a little bit more difficult.
So the second approach, for some bug classes, this works great. We made this work for Java and for C, but for some bug classes, it's really a lot harder to do it with this kind of an annotation, and oftentimes we found that LLMs are actually very good at the task of producing inputs for these targets directly. And sometimes you just have to make sure that the bugs can't dodge this. And so what we did for a second component is what we call Discovery Guy, whose job it was, which is an agentic system that basically has a variety of tool calls to analyze the source code. In this case, you can see it is using the symbol lookup to find functions that are related to the exif tool strings that it found. It collects all of the functions and it looks through the code, looks through the global variables, until it finds that it has enough information to produce a report of how the vulnerability likely looks like. If we look at the report, you can see at the top, we have a call trace where it supposes what a potential path to the vulnerability could look like. And secondly, it includes all of the code locations that are part of this vulnerable chain. What it then does next is, do you want to go next? Yep. Then it produces a report that analyzes the conditions under which the vulnerability. What conditions does the input need to satisfy in order for this vulnerability to be triggered? And it even gives a small example of how this might look in an input, or how snippets of the input might look that the generation then needs. Finally, it will produce a script that produces the input that causes the crash. We will run this input through all of the harnesses in the code, and a lot of the times this is already enough, and it will immediately crash the target. As you can see here, for the Tika bug, it immediately crashed it with just running the input itself. However, oftentimes the LLM is a stochastic mechanism. It's not always correct. It gets something that's close to the correct bug, but not the correct bug itself. So everything we receive from Discovery Guy, we will pass it to a fuzzer and fuzz it for 5 minutes in a vacuum before passing it on to the normal fuzzing corpuses in order to find a bug. Lastly, once the vulnerability is found, it collects the stack trace, and we can see that actually oftentimes matches up pretty well with what the LLM thought the bug would look like and the path of how it get there. And sometimes it finds unintended ways around that are also cool to see. Now, this works great in the targeted setting where we have static analysis results or a diff to guide us. However, when we're looking at full mode targets where there's just millions of lines of code that we're trying to explore, then something like the Discovery Guy is not as efficient in terms of LLM credits of writing one input at a time. So what we harnessed is LLM-guided grammar fuzzing. Now, for our grammar fuzzing, we decided to use another research paper called Nautilus, that is a grammar fuzzer. And the nice thing about Nautilus is that the way you write these grammars is they're effectively Python code, so the LLM has seen tons of it before. And in the case of text-based inputs or simple structures of inputs, oftentimes the grammar relatively clearly reflects the structure of the input itself. However, the real reason we picked Nautilus is highlighted on the left here a little bit. You can write arbitrary Python code as part of your rules to do as complex of logic within a rule as you want. So this really shines in the case of binary inputs that are harder to encode in traditional grammars. And we can see that here, where the LLM was trying to fuzz a compression library, and it wrote an entire Python header function to encode arbitrary tar file headers. And the way it does this is it fills in all the fields. It can even compute the checksum at the end so that every single input that the grammar fuzzer produces has a valid checksum, which is traditionally a hard problem for fuzzers to solve. And secondly, the way these LLMs write code oftentimes tend to lend itself quite well to modularity. So you can see on the right here that it reuses this functionality in multiple different ways to try to hit different functions. And all of the examples you've seen here were LLM written. None of them were written by us. The extent to which you can do this also extends to complex nested file formats. For example, for document files for Microsoft Office, for docx's, you can see that these are zip files with specific logic of XML with specific schemas encoded. And the LLM can write the code to encode these schemas with filled in fuzzable data where appropriate. Similarly, we can do the same thing happens for PowerPoints, where you can see as well, it just produced the code to write these zip files with the correct files. However, one thing you'll notice, and this is something we'll get to in a second, one thing you'll notice is that as it does so, a lot of the expressiveness of the fuzzing grammar vanishes. The LLM tends to hardcode more things. So for example, the types in the XML namespace are purely what the LLM decided to write from its training data, from whatever documentation it had seen. It just hard codes correct things. Wait, one slide back. Back. Yeah, and then lastly, the nice thing about the Nautilus is that we can compose these things. We can have these complex rules, and we can compose them in arbitrary comparisons where we have file formats that it can enumerate, and then that gives the fuzzer the freedom to figure out which of these file formats tend to produce new coverage in the corpus, and which of them tend not to, and then the corpus adjusts on the fly. But as we just said, we have to address this issue with the hard-coded data. And so one thing we did is we augmented the grammar fuzzing with what we call grammar composition, where these file formats in open source projects exist and have existed for a long time. We know what a lot of them will look like, and we can manually write and pre-create and curate a lot of grammars for these file formats already that have that fuzzability property, that are generative enough to really explore the state space within an application. And so when we find these, we create an analysis that would take the grammars that the LLM was writing, try to detect what the file formats were that it was attempting to write. And then, for example, in the top, we can see that it matches a bunch of different file types of known grammars that we have already. And then we will try to insert new rules that allow that new grammar to be spliced into the middle of the old one, which then the fuzzer can take and analyze very quickly and see and explore and see if that actually helped. However, because a lot of this matching is heuristic, we want to make sure that it does something, so we will first run it through the coverage and check that it actually reaches new code before we continue. And lastly, it gets written out. Now, unfortunately, due to a bug in our final submission, this component was mostly disabled. But we're very excited to see how this performs now that we have the targets, because I think there's a lot that we can do here. And we'll put a link to our blog at the end where you can look up once we post the results, because I think there's a lot to find still.
So we've gone through how do we scope the problem, how do we find the initial entry points to actually hitting the bugs, getting crashes, we're drilling down into the program. But remember, the ultimate goal of AIxCC is to patch the program. And so in order to create effective patches, first we have to figure out what went wrong. And that's where our triage engine, the root cause analysis, comes in here. So much like Neo, you can see stopping these bullets, your patches can stop crashes. You can create very shallow patches that can stop each individual crash. But in order to stop the bullets from coming at you all together, you need to stop the guys from shooting you. So the idea is, in order to fix all of these individual crashes that may pop up, you have to find the root cause. Shallow root causes create shallow patches, which will patch the singular case, but not these many bullets you're being thrown at. Incorrect root causes will hinder your patch. If your root cause analysis system is not sound, then you will end up with bogus patches. If you decide to give a root cause that says, hey, the vulnerability or the problem, the root cause is in function A, when it's actually in function B, the LLM will believe you. The LLM will think, obviously it's in function A. Obviously I shouldn't look anywhere else. I'm only going to try and patch that function. So it's very important when you pass the values to LLMs that you give them somewhat correct information. Now, many root cause locations exist on the stack, and stack traces are a great source of information for the root cause. But it's not the only place that your root cause can exist. There are many different bug classes that can be found outside of the stack trace, such as use after free, where the crash location may be miles and miles and miles away from the actual root cause, the actual misallocation, or the actual double free that causes this to happen, right? You really need to answer the 5 whys of root cause, which is you define the problem, what happened, I crashed. And then you have to ask, why is this happening? And then you have to ask, why is this happening 4 more times before ultimately you figure out what the root cause is? So we came up with 2 separate approaches to this. The first one we call Kamushi. Kamushi is a function ranking approach. The idea is to create heuristics based on the information that you have to narrow down the search space of the root cause. Because LLMs are actually pretty good at patching. They have a rough idea of what they should and should not do, and if you can give them locations to look, much like the static analysis that can narrow this down, if you're able to narrow down their function search space, they're able to identify the root cause well on their own. So the idea behind Kamushi is we only give verifiable information, such as the crash report, the ASIAN stack trace, the diff, if it exists, the call trace based on the coverage gathered during the execution of the crashing seed, and then the variable dependencies that happen in the stack trace. Can you figure out where does this variable come from? Why does this variable matter in the actual stack trace? All of this is combined into our first light mode. The idea behind the light mode is that patching takes a long time. Patching is difficult, and if you wait forever for your other analyses to finish, you'll never actually get enough time to patch. So we decided, hey, let's create a quick and dirty, maybe rough root cause estimate that we can feed the LLMs so that they'll be able to generate a patch. Now, in parallel to this, we also run the heavy mode. This is based on another project called Aurora, which does crash exploration. Once you have your crashing seed, we actually try and find as many crashes around it as possible for up to 20 minutes before deciding, hey, I have enough information, I know which functions I can actually crash in, and maybe that gives you more of an indication of where you should be looking. And then we combine that with the prior light mode results to give an ultimate list of around 50 or so functions or clusters, as you'll see, that the LLM should look at. So here's a small example of what the Kamushi output should look like. You'll see that we have a list of what are called POI clusters, POI standing for point of interest. And the POI clusters are really just groups of functions. It's functions that are related to each other, functions that have that variable dependency shared, functions that are executed along the same stack trace. This allows us to not only patch the root cause, but in the case that the root cause exists in multiple functions, or if the actual patch required must fix multiple functions in different places, this allows us to actually see that. This gives the LLM visibility into that area. But sometimes this information itself isn't enough. So we also decided to go with an LLM-guided approach we call DIVA. The idea is we take this POI report, this point of interest report, which is the crash report along with other information, which functions exist in the area, how do they exist in the actual source code itself, and how you can reach them, feed it to an LLM, and then give that LLM several tools, one of them being GDB, so that it can analyze, it can walk around, it can figure out what's going on while I step through this crash. And the other is several tools regarding the source code, which is, can I pull these functions? Can I pull these values that I see? What exists in this other function? Or allow you to set breakpoints in other files based on the function signature. When creating this approach, we noticed that the LLM really liked to take hold if you gave it too much freedom. you would end up stepping infinitely through different instructions, end up dereferencing infinite amounts of stack variables, and going in circles until eventually you ran out of budget. So we realized that we actually had to constrain this. What we had to do was essentially limit how many breakpoints it can set, which variables it can access, what kind of content can it see, and then distill this into a small enough form factor that it still fits within the LLM's context window after executing 20, 30 times. And we designed the prompt of this. We thought, how do we find crashes? How do we figure out what the root cause is? And the idea is we give it information or instructions on how humans actually find the root cause. You give it information of, hey, identify the variable of the crash, and then walk backwards. Try and figure out where this came from. Look through the source code, figure this out, and come to an ultimate conclusion. So you can see here a GIF that'll play of the Diva actually running, where first it generates a plan, and then it starts looking through source code to try and identify where it actually needs to start setting breakpoints. It'll then set some breakpoints. You'll see in a second here that it starts looking through different values at the breakpoint that it ultimately hit. And then once this runs its course, it'll come up with a root cause report that maybe looks something like this, where it'll identify which potential bug classes that can happen here. Here we have a OS command injection generated in the Tika project. You get a function location, you get a line location. It gives a general description of what the root cause is. Now, we also gave it a couple other fields that may have been interesting. We tried giving it the ability to describe which patches it thinks would fix this location. And actually, ultimately, that turned out to be a very bad idea. Just giving the LLM the information of what it thinks the root cause is enough for the later patchers to discover where they need to explore. Whereas if you try and give it a suggestion for a patch, much like I had said earlier, it goes directly down that route. It cannot be steered away. If it's somewhat incorrect or somewhat shallow, then it will stick with that, and it will not take no for an answer until it ultimately generates a patch. Which brings us to our patching. So now that we've identified the root cause, we can try and fix it. Our two patchers, Patcher Y and Patcher Q, their job is to eliminate the bug, like Agent Smith here. And if you give them the understanding of the root cause, they can eliminate that bug very, very well. Here's a quick example of one of the exhibition challenges, one of the diffs that was released in lead up to the finals, where you can see I have highlighted in red an unsafe use of the size of function, where ultimately this will lead to a buffer overflow somewhere. So keeping this in mind, let's say we have a crash that reaches this location. Let's say we have a nice root cause that says, hey, your size of keyword, this is a problem, this is an issue. You're getting an overflow somewhere. So what are the steps that you need to take to make sure that your patch is good? So first off, you give it any sort of code context you have. If you have the diff, fantastic. If you have the root cause location, fantastic. If you have any other sort of tertiary information regarding where it should look, like the POI clusters given by Kamushi, fantastic. Then you give it the stack trace. You say, hey, explicitly, this crashed here. This was the reason. I had a buffer overflow, because the bug type matters. The bug type has a lot of encoded information of which type of patch it should generate. And then you also need to give it several other tools. Like we've mentioned with some of our agents before, it needs the ability to run around the source code, to grep for functions, grep for files, grep for patterns. And ultimately, this gives you a decent patching solution. But once you have your patch generated, how do you know it's good? So the first thing, your patch has to compile. If your patch doesn't compile, then it's worthless. And then you have to run the tests. Luckily for AIxCC, we were given some intrinsic tests that we were able to run to validate, hey, beforehand, these tests executed no problem. Afterwards, there were some issues. Afterwards, one didn't run, or afterwards, you got a warning. You need to make sure that when you apply your patch, there's no issues. There's no new information that the tests give you. And then finally, make sure your crash doesn't crash. If your crash still crashes, then you're toast. You didn't generate a good patch. You just wasted tokens. But how can you stop that from happening? How can you stop wasting tokens? So here you can see we wasted some good tokens. We generated a patch using just this information, and while we fixed the crash, while we compiled, while the test case passed, the patch decided to hard code a length of 80 into the buffer and return early with a read length greater than size of keywords. Now, this fixes the initial crash. We no longer crash, but if you have any other type of change, any other maybe lengthening of the input or other data fields, you will see another crash. This is a bad patch. This does not fix the root cause. This does not fix the problem. So how can we make our patches a little bit more robust? There's two methods that we've implemented for doing this. One is extra fuzzing. So take AFL and fuzz the patch that you generate for 5 minutes. This invalidated more than 50% of our initial patch generations. This allowed us to see initially, hey, I didn't actually fix the problem, I just made it go away for a little bit. And so in doing this, we also generate new inputs that when we do another feedback loop of this patching, we can say, hey, test all of these inputs we found as well and make sure that you don't crash there. And then you can avoid this extra 5 minutes of fuzzing again multiple times. And then we also have bypass guy. So much like how Lucas had said initially with discovery guy that's able to one-shot generate proof of vulnerabilities, we try and do that with our own patches and say, hey, I generated this patch, can you fix it? Or can you get around it? This is something that we need you to reach. And if you manage to complete all these steps, you get a nice functioning patch. You say, hey, patch is verified, let's go. But something that's interesting is, and this is ultimately the patch that we generated, you can see we get rid of that nasty size of keyword misuse. And we just say, hey, your read length max, it should be this value that we set beforehand. Something very interesting to note here is that generating patches is hard, not only for computers, but for humans too. So we were also given the ground truth by the organizers of the competition. And as it turns out, you can see this is some of the code they added for the SQLite challenge, where we access some some array values and ultimately we write a Z somewhere. We were able to bypass their patch for this. They had this patch, which you can see there's some commented out thing here where they tried to estimate the value or the size of this buffer index, something like that, and then recalculate it to this 4 times BN number. But we were able to bypass that with our own bypass agent. So this is something that not only machines need, but humans need as well.
All right. And then the last component that I'm going to talk about real quick is for the game infrastructure, we also were required to do deduplication specifically on the patches. So the first part that we do is we have to identify, we do some deduplication on the crashes just in order to make sure that our patchers, when we give them new crashes to look at when they bypass one, that the next one they get has different information. The second thing we have to do, not only do we usually have to deal with one crash per vulnerability, but we get multiple of the same one. Over and over, and we can't do anything statistical, just like randomness, because sometimes there's one crash that's CPV2 that hides in the noise of all of the different crashes that we find for the first vulnerability. So what we do is we do patch-based clustering, the intuition being that one patch that eliminates multiple crashes shows that they're from the same bug, and any patch that fixes more crashes is more likely to fix the root cause, resulting in the obviously final solution of this where you have a perfect patch that fixes all crashes in a cluster. If we have this, we send it to the organizers. Otherwise, we give it in a refinement loop back to the patchers and say, create me more patches. The cool thing is that this kind of mimics the state-of-the-art deduplication in industry, which is humans write patches, see if the crash goes away, and then commit it. And then LLMs make this automatable. And if we do this correct, then eventually we can finally achieve our goal and eliminate all of the Mr. Smiths in the program and find all the crashes. Awesome. Thank you. This is our talk. Any questions? Feel free to ask them now.
大家有没有问题？那我这边问一个问题哦，我想这个问题我先用中文跟大家说明一下。这个问题是，其实 Shellphish 是一个 CTF 很强的队伍。他刚刚也说他们去打胖多翁，各位想不想知道以后我们去打 CTF 的时候，他们要不要用这个工具带过去？那我们还打什么？所以我想问这个问题。Shellphish has been a very top CTF team, and you have been also competing in Pontoon. Do you think this tool is something you would actually bring to the human DEFCON CTF and the Pontoon competition? And would it be helpful there?
Yeah, I actually think absolutely it would be. We competed in the DEFCON CTF finals just earlier this week. And prior to that, we had spent a week trying to port our own CRS to work with binaries. Because of course, with AICC, it was all working with source code. We saw real promise with having it work with binaries. We saw old CTF challenges that we were actually able to find the exploit with Discovery Guy, able to one-shot the location to actually crash it. We took our root causing agent and combined it with decompilation so that we were able to actually have some sort of source level-ish debugging, and found that it was pretty okay at trying to reason about these sorts of challenges. So I think, yeah, very reasonably, you can apply this to real world situations.
What rank you got?
This?
Yeah.
We got 5th place in AI Cyber Challenge.
No.
In the CTF.
Yes.
Not last.
Okay. Thank you. 大家还有没有什么问题 ？Okay, come on.
I love the metric theme. It's a good metaphor for the context. Thank you for that. And I want to know, I want to ask, this AICC competition, it gives you, you basically fuzz it and you find a POV and then you generate a patch. It's like giving the cursor the context to fix a bug, and then it goes off and it fixes it. And what if we do it in reverse? We give you a patch and you generate an exploit. Would this be easier in your opinion? And how would you approach it if there's another AICC for this? Thanks.
Yeah, so I mean, I think in terms of the being given a patch to a specific vulnerability, that's actually already kind of incorporated in the design through the Delta mode, where you apply some changes and you want to know, is there bugs introduced or missed by that patch? Is the patch not exactly fixed? And as we talked about with the bypassing of patches, we already do this in the setting where we have the LLM go back and try to regenerate a crash that bypasses that specific patch. I think we'll have to see how this develops. I think we've seen a couple cool ones, even just with Cursor. The thing I thought Will was going to mention was one of the CTF challenges at DEF CON was automatically solved by Cursor with a little bit of human intervention in like 10 minutes. So I think there's plenty of stuff in terms of being given a patch that doesn't actually change that much for us in terms of the current setting.
Okay, so you think it's like trivial to repurpose your system into generating exploits?
Yeah.
Okay.
So into generating full-on exploits, no. I think there's more that needs to be done in terms of visibility. I think generating initial crashes is a lot easier than generating a full exploit because you need to understand the full memory layout for memory corruption exploits, that kind of thing. So I think that there's going to be more research needed to do more cyber grand challenge things where you're trying to actually generate full exploit chains to some degree. Right. I think that's a little bit further out still. We're still having to look into how to do that, but the crashing part I think is pretty much, I mean, not done, but it's very good already.
All right, thanks for your answer.
OK， 好，我们时间已经到了，我们再次掌声感谢 Shellphish。